start. So Professor Arindam Ghosh is a professor in the Department of Physics. He did his PhD at the University of Science on probing metal institutor transition and Coulomb interaction effect in dope semiconductors in 2000, following which he went to Cambridge University in UK as a postdoctoral researcher. His current interests include the transport properties of one-dimensional electronic systems in semiconductors, carbon-based low-dimensional systems, optoelectronic properties of atomically thin semiconductor membranes, magnetic nanostructures, and structural stability of nanoscale systems such as metallic nanoparticles and nanowires. He has published more than 100 papers in international journals and conferences, including Physical Review Letters and Nature Physics. He is a member of the American Physical Society, Indian Physics Association, Program Review Committee of the International Center for Theoretical Sciences, and Advisory Committee of IOP Publishing Asia Pacific. He has received numerous awards, including the UK India Education and Research Initiative Award 2006, IBM IIScTF Visiting Fellowship in Nanotechnology 2008, Swarna Jayanti Fellowship in 2008, the Material Research Society of India Medal 2012, and the Shanti Sharup Bhatnagar Prize in 2012. So without further ado, I would hand over to Arindam. The title of the talk is Exploring New Material and Device Paradigms for Quantum and Related Technology. Over to Arindam.
Okay, thanks, Sanjay. Let me just share. Let me see if there's a problem. I should be able to share it. Screen. 2. Can you just see if you can?
Yeah. It's visible. Yeah, it's visible.
Okay.
You can start.
All right.
Yeah.
Thank you very much. First of all, thank you to Prashanto for giving me this opportunity. It's, we often, whenever we speak a lot about quantum, we usually restrict our discussions towards core quantum technologies, which we have been listening to many very eminent speakers here, and also, computation algorithms, various kinds of quantum optical experiments, etc. But often the device and the material paradigms are ignored simply because they do not come directly under a particular head. That's what I'm going to talk about. It's of course very difficult to speak about everything, but what I'll do is there are young people here. I'm going to give an overview first, tell you what today's paradigm or today's understanding of quantum materials and devices are, because it's sort of an emerging concept in itself. You'll see quantum materials is being used often. So I'm going to give you a little bit of example of what we mean by that. And then in the second half of this presentation, I'm going to give a couple of specific examples, which is connected to my group about what's going on. Okay, so I don't have to really finish everything, but I'll finish. So I'm going to stop at 45 minutes. Okay, I'm guessing, let me just quickly my pointer. Yeah. So Chiranjeev, can you tell me if you can see my pointer?
Yes, we can see the pointer.
Good, excellent. Thank you. Okay, so by now you would have all got the idea that quantum technology in particular is essentially based on three core verticals. One is quantum computation, communications, sensory, and metrology. And I don't want to go into the detail because you already know there are enormous number of promises that comes with quantum technologies. For example, you have navigation systems, ultra-precise clocks, which are already now in place. Simulators for drug design, sensing. You can have huge different impact in sensing in diverse vectors, from oil gas exploration to geodesy and then medical imaging. So there's a huge amount of activities are possible and applications possible with the newfound capability and exploiting unconventional capabilities of quantum mechanics with or without entanglement. Of course, secure quantum communication is one of the major directions that we all know about. And last but certainly not the least is quantum computations. Okay. Now, all these are very good, but you need a workhorse, right? So you need something where you will try all these applications. As a result, quantum computing technology is built on this entire verticals of quantum material and devices. Now, what I'm going to do is initially give you an example of what is the demand of all these core three technologies on the quantum material and devices sector, right? For example, if you take single photon detection is one of the major activity or a major requirement for quantum technologies. For example, in communication, you will require single photons to be sent from Alice to Bob, and it's a discrete variable, so you can use the polarization of the single photons as your state variable. But then you need to have sources and detectors of these single photons, which will tell you whether there's a hacker in the channel, right? So that's a bird's eye view, and we need single photon sources and detectors for that. In the computation, of course, you need single photon detectors, of course, sources and detectors with another dimension. For example, if you want to look at Gaussian boson sampling, you need detectors which can resolve the number of photons in a particular pulse of light. So, for example, if you've got n photons and you make them go through the interferometers and then your detector and all these detectors here, you need single photons, these detectors, to be able to tell you how many photons have reliably hit the detector in order to complete the entire Hilbert space. So there is another characteristics of these detectors that you would like to have. They should be able to detect the number of photons. So you need number resolving single photon detectors. Third, and in the sensing and metrology, for example, if you want to use it in a quantum radar or something of that sort, you will require a single photon, and you keep the idler photon, and then you make the signal photon comes back, and you compare the entanglement property of the idler and the signal. These are protocols, and there are various forms of these protocols, but this is overall idea. So you can see the number of cases a single photon detection technology becomes important. Now, where are we with the single photon detection technology today in the market? So, for example, a photomultiplier tube is one of the major original single photon detection process. It can work at room temperature. It is very fast. It's 10 megahertz. You can weakly resolve photon number, but it's not particularly reliable all the time. Okay, but the efficiency is very low, just about 2% if you look at the telecom wavelength. That's about 50 nanometer or so. Okay, and you need to apply very large voltages in order to make these single photon cameras work on the photomultiplier tube. All right. Another very important technology is the avalanche photodiodes, which is often based on silicon or low bandgap semiconductors, like in indium gallium arsenide. So they work very well at the communication wavelength, which is about 50 nanometer, and they work at good efficiency, about 30% or so. It's easy, it's very small, and also there is, they work at close to room temperature, at least the silicon ones for sure. But the number resolving properties. So you can use them for certain applications, but you cannot use them for everything you can think of. Okay? The ones which are used mostly, for example, in photonic quantum processing, as well as various other applications, are the single photon detectors based on superconductors. And there are two different types. For example, the transition edge sensors, as well as the nanowire single photon detectors. They work at a very high frequency, and in the telecom wavelength, about 1550, about 90% efficiency is possible, of which SNSPDs do not have the number resolving properties, but TES, the transition edge sensors, do have number resolving properties. Unfortunately, though, they are very slow. Now we are talking about 100 kilohertz frequency, whereas you can see the photo multipleters were 10 megahertz. So, and also, of course, if you are using superconductor, the things become very, it's low operating temperature. So you cannot, they are not very portable systems. But even then, I mean, the single photon detection technology is going up so fast. You can see that recently, all the numbers of SMSPD systems sold. This is unconfirmed report, but they are increasing very, very fast. I mean, this is till 2019. Actually, they have increased even more over the last 3-4 years. Okay, so what we need is a technology, or we have to continuously evolve our material and devices base for these kind of techniques in order to cater to all the very stringent requirement of the quantum technology verticals. It's not just single photon detection, but also single photon sources. If you look at the single photon source technology, in computation, communication, sensing metrology, there are various optical components, and single photon detection and sources are just one. So in single photon sources, you also require a series of extremely stringent properties. You need a fidelity of 1. You need to be deterministic. That means every time you need a single photon, it should come out. You need to operate them at the telecom wavelength of 1550. You need very high brightness. You need at least 1 megahertz, about 10 to the 6 photons per second. You need high purity. You need to make them operate at room temperature, and you need to them to be indistinguishable. So you can see the kind of restrictions that you're putting on each and every aspect of these components of devices. Okay. As a result, there are just on single photon detection sources, there's a huge number of material-oriented research that's coming up. Say if you want to do spontaneous down conversion, you are continuously looking for new material with a strong nonlinear optical properties. In addition to that, you are looking for other kind of sources like quantum dots. They are usually very high brightness sources. Then you are looking for nitrogen vacancies. So all these come under various forms of material and devices verticals. Okay. Now, if I look at I should keep it tie on my time. Okay. Oops. How much time did I take so far? It's about 10 minutes, right? Okay. Okay. So I'm going to give you a bird's eye view of what's happening in the overall material base for quantum technologies, and these can usually be divided into 4 or 5 different classes. So research is happening in semiconductors, because I'll tell you where semiconductors are becoming important. There's a whole new class of 2-dimensional materials. There's a class of topological materials, and of course, superconductors. Okay. So in terms of semiconductors, you see you need qubits, and there is a new improved and structures of qubits are coming up all the time. This is an example of strained silicon qubit. This is on a silicon germanium platform. You are immediately going to be relevant for the computation and sensing metrology. Semiconductors are needed for single photon sources. For example, the gallium indium arsenide-based quantum dots, and which are enclosed in a Bragg mirror, are highly efficient entangled photon sources. They are going to be used in photonic quantum processing, quantum communications, as well as quantum sensing metrology. We need semiconductors to make our interferometers, correct? And where you need these semiconductors to design our waveguides and make the phase modulations on chip. So this is a major use in the quantum communication and sensing metrology. Then we have detectors. Of course, semiconductor-based detectors are essential for all 3 verticals. And then something that we always ignore, look, at the end of the day, you need to make the classical and quantum interface, correct? You will process the information in the quantum domain, but you will still need to read them out with the classical electronics that you have. And semiconductor is the backbone of the classical electronics. So we need to create devices which are better and does new activities. For example, neuromorphic computing, for better packaging for semiconductor electronics itself to interface with the quantum world in a more efficient manner. But semiconductor is one, superconductor is of course another. We all know the superconducting based qubits are one of the forerunners as the key platform for quantum technologies. But there are continuous evolution even in that vertical. For example, okay, we all know aluminum oxide. Aluminum is one of the Josephson junctions, but there are, there are advances in which you have granular aluminum, for example, as a source of Josephson junction, because there the granularity and the weak connections between the grains act as natural Josephson junction, and you do not need to have additional components of oxides. And that is actually, I'm going to show later, that's often the substrate, the oxides, etc., are sources of noise, because those can have low frequency noise that can dephase, that can cause decoherence in the qubit itself. Of course, you need new superconductors and a high density of superconductors to make your single photon detectors, which I told you about. We also need new type of superconductors to form whole new concept of qubits, which are often called topological qubits, where unconventional superconductive pairing can lead to intrinsic protection of the qubits from the environmental disturbances like the decoherence and so on and so forth. We would like to go to higher temperatures, of course, and this is where the BISCO and high TC based superconducting Josephson junctions are now being extremely heavily researched, and we are getting new types of platforms. Okay? And then finally, of course, you are talking about quantum computation, communication, sensing, but you also look at completely different domain where you can take these superconducting technology into dark matter detection and various other exotic and interdisciplinary applications. Now, these are superconductors and semiconductor, which are the major directions of material directions for quantum technologies. I would like to touch upon a little bit on the concept of topological materials, simply because this is often a very mysterious term, and what do we mean by topology is going to be non-trivial, and people often ask, so what do we have to do? Why we need topological research and development of topological matter, which is often called the quantum matter, for advancements of quantum technologies in the first place. So I'm not going to be able to give you a full snapshot of this because it's a very broad field, but usually topological matter is composed of 4 or 5 different classes of material, and which have kind of come up over the last couple of decades or so, where you usually use a very unconventional property of the electronic wave function in order to create some functional aspects. For example, if you look at Dirac semi-metal, the electrical bands of an electron in the solid where it behaves as linearly with momentum. Energy goes as linearly with momentum rather than parabolic, which is a standard metal semiconductor. And this comes because of a certain wave functional property of the electrons in these materials. All these materials usually utilizes crystal structure, the symmetry properties to have these properties of unconventional nature. So let me give you an example of this niobium phosphide thing, for example. Okay, so this is a wild semi-metal in which you have a 3D. In the 3D, the bands of the electrons are linear, like something like this. So niobium phosphide has a electronic bands which have got this linear electronic bands. This is energy of electron as a function of momentum, and where you have this linear bands in the Fermi energies, the Fermi energy. you can compare or look at the difference between that and the conventional semiconductors. You can see the semiconductors have a parabolic band like this. Okay, whereas in the other case of Dirac semimetals, you have got this kind of cadmium arsenide or tantalum arsenide or graphene. I'm going to come into in a few slides, have this kind of linear band structure. Now, why this is such an important thing, such an interesting property? Because of the linear band structure, the electrons in these materials can actually go around the disorder very easily. Okay, so they can bypass the disorder and they don't get scattered by the disorder very easily. As a result, what happened is these electrical mobility of charges in these materials can be extremely high. You can see the mobility is usually expressed in terms of centimeter square per volt per second. You can see the mobility can be as high as 10 to the power of 7 centimeters at lower temperature of about 50 kelvins or so. If you look at, if you compare this with, say, gallium arsenide semiconductor structures, which is one of the highest mobility semiconductor structures that we have today, it took me over 30 years actually to come to the stage of gallium arsenide based, mobilities of 10 to the 7. So, and that's because there the mobility is entirely determined by how clean your system is. How disorder-free can you make? So that's an incremental steps that we have taken over the last 30 years that has allowed us to get extremely high-quality gallium arsenide heterostructures. But in the case of niobium phosphide, because of the intrinsic protection of the electrons against disorder, you are able to get such high mobilities with relative ease and rapidity. Okay. So as a result, you are talking about these unique materials with certain unique electronic structures and hence certain properties. And we can now look at certain novel superconductors which can have p-wave pairing symmetry, which can have probably what you call Majorana modes at the centers, and they can lead to fault-tolerant quantum computation. So those are one of the directions, some major directions of research. We can have novel physical properties. You can, as I told you earlier, they can have enormously high electrical conducting mobility. You can have large magnetoresistance. We can have new kind of sensors with those magnetoresistance, photogalvanic effect, new kind of magnetism. You can use them because they are often their electronic properties are often determined by the fundamental constants like Planck's constant, like the electrical charge. You can use them as standards. You can resistance standards and use them in GPS positioning systems and so forth. And also there are possibilities of new qubits that still are being thought of. Okay. Of another component of what I would like to talk about is 2D materials, because this is something which I work on. There are a lot of people are very excited by the 2D materials. 2D materials have got a large number of members. Graphene is the first one. Then you've got dichalcogenides, molybdenum disulfide, or bismuth selenide, or some of the oxides for high-tensor superconductors are also layered materials. Basically, the idea of 2D material is that if you have graphite, you can separate them because they are very weakly bound to the next layer. So these are called layered materials. Compared to, say, covalent bonds or an ionic bond of carbon tetrafluoride or sodium chloride, these are much weaker, so 1,000 times weaker. Okay. As a result, you can make these materials in a single layer. And just to give you a snapshot of graphene, and I told you that why these unique band structures can be developed. 2D material is one of the members of the topological materials or quantum material that I talked about. And you'll see there that because of the unique crystal structure, the electrical energy as a function of momentum becomes very different from standard systems. For example, in the case of graphene, if you simply take tight binding model, in which on a hexagonal lattice, and you take the p orbital, pi electrons, and because those are the low energy electrons that are available for most electrical properties and other physical properties of graphene, you will see that simply solving the tight binding model gives you the energy eigenvalues directly proportional to the momentum k, which means that at every point of this hexagonal Brillouin zone of graphene, you have this energy of the electrons varying linearly. And it means that every electron behaves like a photon. But the photon, of course, in this case is an electron or effective quasi-particle with much lower velocity of about 300 times lower velocity than an electron, than an actual photon of light. So this is one of the unique properties of graphene that led to a lot of work over the last 15 years. Now, it's not alone. Graphene is certainly not alone. And another very prominent member is molybdenum disulfide or transition metal dichalcogenides. The difference between molybdenum disulfide and graphene is, apart from the fact that you can, this is a molecule rather than a single based on carbon atom, you can still take out one atomic layer of this molybdenum disulfide and make an electrical circuit, because graphene has got a conical band structure, which means there is no band gap in graphene. But in the case of molybdenum disulfide, it's a semiconductor. Okay, it looks hexagonal, but molybdenum and sulfur from the top looks something like this. It's a trigonal prismatic structure. But because of this unique molybdenum and sulfur orientations, you have now molybdenum disulfide is a semiconductor, which is very similar to silicon, except for the fact that silicon is an indirect bandgap semiconductor. But in case of single layer molybdenum disulfide, it's a semiconductor which has got a bandgap of about 1.9 electron volt. And this makes a wonderful optoelectronic element. And this has been something which we have used in our work, that if you shine light, then electrons can be excited from the valence band into the conduction band of molybdenum disulfide, and you can make extremely efficient optical elements for quantum technologies. I'm going to come to that later. Now, overall, I mean, these two-dimensional materials can have a huge number of different possibilities of electronic band structure. In case of graphene, you have seen this conical band structure. If you use bilayer graphene, there are two graphene layers on top of each other, then the two layers interact with each other, and that interaction immediately changes the band structure, and it now becomes parabolic, like a standard semiconductor, but without a gap. But then you come to molybdenum disulfide type of structures, where you now have semiconductor-like beautiful parabolic band structure with a band gap. But then you go to bismuth selenide ones, and there they are called topological insulators, where you have got a band structure like this in the bulk, but the surface is like graphene, like a metal. So there's a whole spectrum of these kind of systems that is now available. And it's now told that there are probably 1,825 different types of exfoliable materials of two-dimensional type. So you can see there's a huge amount of possible phase space that we can as a material scientist or physicist, we can cover and explore. Now, what about quantum technologies? So where does 2D material come in quantum technologies? And for example, you can go to high electronics with high mobility and low power FETs, of course, and that's heterogeneous integration into CMOS devices have already started taking place. We can make novel superconductors with unconventional pairing as one possibility. You can make topological matter, for example, those with broken inversion, and lead to new states along the edges of these materials, and those can host novel electronic properties. We can directly implement them in quantum communication as quantum emitters. It has been shown that the defects in two-dimensional materials are wonderful single photon emitters, and it has been the defects in transition metal dichalcogenides, the boron nitride, they work at very high temperatures. They are also being used, and this is what my group has been involved in making single photon detections or photon counters using two-dimensional materials. And you can make number resolved single photon detectors with this. We now have a single photon microwave detection, particularly for circuit quantum electrodynamics. You can measure single microwave photons. It's still about at a 30 megahertz, slightly high. Now the noise in such devices are continuously coming down. So you can make, because graphene and two-dimensional materials are just one layer, you can use them as wonderful bolometers, because a tiny amount of heat can change the temperature very much, and you can detect them through their electrical properties. So this is a key advantage of two-dimensional materials because of the mass and low mass and specific heat. And also the quantum sensing with spin defects in boron nitrides and magnetic sensing are directions that's coming up very, very rapidly. Okay. I want to tell you a little bit about my group, what we are doing. We are working on various kind of devices. For example, devices that we are working on are those which look at the noise in quantum devices of various types, particularly those which work on for quantum technologies. For example, if you see noise, you will see that the noise not only limits the signal to noise ratio, but it also causes dephasing in quantum devices, as dephasing in qubits, for example, and also in photon counting devices, and for which you need new architectures. Usually these noise are low frequency noises. For example, as a function of time, you see in the order of seconds or milliseconds, you see these random fluctuations. Usually this is called 1 over f noise. They are quite useful in some other purposes also, but I'm not going to talk about it. I'll give you an example of what we have done in minimizing and understanding noise. See, the noise is one of the key problems that has been outlined in material challenges for quantum computing hardware. Because what happens is that noise will give you, it will reduce the fidelity dramatically, and it's positioning the state vector essentially wanders on the block sphere if you've got noise. Let me tell you how. So suppose you have something like a block sphere of making a qubit with aluminum oxide, aluminum junction, and suppose it couples to one two-level system. A two-level system is essentially could be a cluster of atoms in the aluminum oxide, for example. And these cluster of atoms are not stable because aluminum oxide is not ideal. It's an amorphous region. And that cluster of atoms moves between two positions. And every time it goes from one position to the other, it can either emit phonons or it can couple to the state vector through some piezoelectric or dipole interaction. And you can form a Hamiltonian of the coupled to the block sphere and the two-level system. Now, when this system is coupled to such structural two-state system, any kind of observable reflects in these two types of states, which are called random telegraphic noise. Okay, so this noise is called random telegraphic noise. So if you take a power spectral density of this through an autocorrelation function, then you get a noise which is like a Fourier transform of the autocorrelation function, which leads to a Lorentzian type. The Sx is essentially a power spectral density of the single fluctuator or a two-level fluctuator, which is in the vicinity of your quantum of the qubit or the Josephson junction. Okay. Now, in a real system, of course, there are multiple fluctuators. There's not one. And those multiple fluctuators will flip at different time scales. Okay, so you need to add them all up. So you need to add all the Lorentzians of different time scales. And then if you add it properly, you will see that the frequency dependence of power spectral density goes as 1 over f. Okay, and this is called 1 over f noise. Why am I worried about 1 over f noise? Is because as the frequency goes to 0, the noise actually diverges or it becomes very, very high. Okay, why is that important for our quantum-enabled devices? Because if you look at the control field and the stochastic field comes because of these disturbances in the environment, it's not very difficult to show that the autocorrelation function of the stochastic field will cause the quantum information to decay with a time scale of tau phi. And the T2 times essentially is now determined in certain situations by the phase breaking time or the tau phi inverse, where tau phi inverse is essentially the zero frequency power spectral density of noise. And as I said, 1 over f noise diverges. So that means that T2 time becomes really, really small. So we do not want 1 by f noise in our systems. Okay, example. This is a work that came out from the Sydney group in silicon when phosphorus atoms form qubits in silicon. You can see these two tiny phosphorus atoms. These are the qubits, and this is a semiconductor-based quantum, quantum computing platform, which is this phosphorus doped silicon. And this kind of materials have got extremely long T1 time, and single qubit T1 time of about half a second. We looked at their noise properties, and this work was done in collaboration. These materials have grown in a wonderful, very interesting manner. The way they grow is essentially they incorporate individual phosphorus atoms using scanning electron microscopy by surface passivation, and then you remove certain passivations from somewhere, some points. You incorporate phosphorus atoms, then you grow silicon on top of it, and then you have essentially silicon exactly where you want. Okay, so this is how the qubits are made. So each of these two phosphorus atoms are like two qubits, which interact with each other through exchange interaction. Okay, we measured electrical noise in such systems, and we found that these systems have got the lowest noise in nature than all systems of this dimension. For example, if you make these phosphorus atoms along these lines over here, and you measure their properties, noise properties, this axis is noise magnitude. You can see this is a one-dimensional system. You can take many other one-dimensional systems like nanowires, like carbon nanotube, like silicon nanowires, and we found that the noise magnitude is the lowest, which is what is directly reflected in the extremely long T1 time or the dephasing time in these properties. Now, this is one direction. I was talking about 2D material. There's a very steady progress towards the graphene-based qubits now. And the graphene-based qubits are essentially built right now on the bilayer graphene. Okay. What happens is here, you encapsulate bilayer graphene in between two layers of boron nitride. You apply gates from top, and by applying gates, you can make these 2D, you can make these quantum dots. Typically, a device looks very complicated. This is a paper which came out from Christoph Stamper's group in Basel, I think. And you can see very, very, very complicated gate structure. Now, I'd like to tell you what is the property of the bilayer graphene that actually enables you to form the qubit or the quantum dot in the first place. See, graphene has a lot of advantages. Graphene has got very weak spin orbit coupling, so the dephasings and you can make carbon extremely pure without too many magnetic impurities or atoms without magnetic moment, so that you can actually look for very high dephasing time. So which is why many people are trying to look for this kind of platform for qubit formation. So, but in case of bilayer graphene, there's some unique advantage. Suppose, what is bilayer graphene? Bilayer graphene essentially is two layers of graphene, which are separated by about 0.3 nanometer, 3 angstroms distance. Now, what happens is that if you assume that these two layers are independent of each other, then they will have graphene-like structure or electronic bands like these tonical bands I told you in the beginnings. Okay. Now, if I apply electric field about perpendicular to the plane of bilayer graphene, what happens is these two cones of the two layers start shifting with respect to each other in the energy direction. Okay, so that's how this has moved. But now what we do, I switch on an interaction between the two layers because they're so close to each other, the electronic bands overlap. And as a result, there is a coupling between the upper and the lower layer. And the moment you start that on, you will see that there is band gap that opens up in the electronic structure. And if you make the coupling very strong, then you get parabolic bands, which is tunable by electric field that you apply. So which is very nice, because what you do is that from the same platform with a bilayer graphene, certain regions you apply electric field that opens up this band gap and that creates these quantum dots. So you open a band gap in this region, you open a band gap in this region, you open a band gap in this region, and you essentially make sure that there is no band gap, a small band gap in this and this. This is your source and drain. And this is a quantum dot, another quantum dot, which can have a single electron in them, which you can use for forming your qubits. So this is the overall idea of how graphene is being used directly in the quantum computing platform. So naturally, if you want such systems to come in a quantum processing, you need to know what their noise is. We have been using this, measuring noise in these systems. We find the substrate is extremely important where you keep, and this is why often you encapsulate graphene in boron nitride kind of insulating substrates. You can see the noise. This is the noise magnitude is extremely large when the graphene is kept on amorphous substrates like silicon oxide, but the noise comes down dramatically if they are kept on the boron nitride kind of substrate. In addition to that, we find the contacts are extremely important, that you need to have non-invasive contacts in metal contacts in order to reduce the dephasing and the noise in two-dimensional materials. Overall, our understanding over the last several years on this topic shows that there are lots of new noise sources, which is why we need to improve the devices. We need to improve the traps in the substrate. We need to improve the channel mobility. We need to use the proper contacting strategies. We need to make the single crystalline, and of course, the interface of the metal and graphene requires to be. So all these work we have done over the last 2 years have allowed us to come to an optimal strategy of creating ultra-low noise graphene devices, which now has a record low noise in literature based on two-dimensional materials. Okay, but in the last 5 minutes or so, I think I have that much of time. What I'm going to do, I'm going to take a turn and I'm going to show you that, look, our ability of tuning bilayer graphene's band structure. And this is why the novel devices or device research comes into play. The same ability of bilayer graphene, which allows us to make qubits, can also give us rise to fantastic photodetectors, which we can use for single photon detection. Okay, I'll give you an example. Okay. Second, yeah. So for example, if you look at single photon detection technology today, it's usually, if you look at as avalanche photodiodes, you have a region of receiver and an absorber and a receiver, and there's an amplifier region. This is where the electrons go and they collide with ions and they create a lot of holes, and the amplification happens of the number, the gain, optical gain takes place, and a single photon gives you a measurable current, right? Now, if you ask the question, where does noise in these kind of these kind of architectures come from? There are usually two sources of noise, and this is given in this signal to noise ratio. This is called the excess gain, which is essentially the gain noise, where it means that the combination of the electrons and the holes in this amplifier region is stochastic. That leads to excess gain noise, and that limits the signal to noise ratio. And another is the noise in the channel itself, which comes from dark current. So one of the things that you need to do is to reduce the dark current. Okay. Now, gain noise actually can you can't go to infinite gain, because after some time, gain noise and the signal to noise ratio increases simultaneously. So there's no point in going to large gain. But what I'm going to do is that we will find a technology in which both gain noise and dark current can be reduced. Now, in order to do that, what we did some time ago, we created a structure where the graphene is sitting next to a transition metal diagonal. I told you about graphene, which which conducts electricity very well because it has a band gap, it has mobility. But in the case of transition metal dichalcogenide, which is a material which has got a band gap, you can use it to absorb light. So that's a wonderful property to have. And if you put them together, then what happens is that molybdenum disulfide is the absorber region, which is the absorber region in your avalanche fluid diodes as well. But then the absorber region gives the electron to graphene region to electrically conduct the current. So as a result, the conduction region and the absorber region are physically separated. If you look at the avalanche photodiode convention with structure, the absorber region and the conduction regions are the same. As a result, you get gain noise because of stochastic recombination. But now, if you create a structure like this, where graphene is sitting on molybdenum disulfide, and you measure the electrical property of the graphene layer alone, then these two regions become physically separated. As a result, the gain noise becomes very, very small. But the problem is with graphene is that it doesn't have a band gap. As a result, the dark current is very high. Okay, and as a result, the noise is very high as well. So what we did now, we did exactly the same, which the quantum computing guys were trying to make qubits with graphene electrode. We essentially applied an electric field across the bilayer graphene between the top gate and the back gate voltage, where the upper gate is the graphene and the lower gate is the doped silicon, and that opened a band gap. Now, because of the band gap in this, I can still transfer electrons from the molybdenum disulfide layer, but because of the band gap, the current becomes very small. By the way, this whole, I'm showing these cartoons, but these are complex devices to make, and these are usually called van der Waals heterostructuring, which is used in many of our material engineering strategies, in which you take materials layer by layer and put them on top of each other in a sequence that we want. For example, here, this is how the graphene, bilayer graphene MOS2 photodetector was created. This is a layer of MOS2. And this is the whole thing you can see is created the bilayer graphene. This is molybdenum disulfide and the graphene on top. Okay, and we have been able to measure the single photon detection with this. You can see this is the pulses of light. These are pulses of light, and the current in the bilayer graphene reduces in steps, and this current is directly proportional to the number of photons that have been absorbed. So change in IDS, and we know how much how much current change one photon will cause. And you can see the number resolved photon detection, where you can, from a very weak source of light, we have been able to detect the single photon, what do you call this? Single photon emission properties, the Poissonian statistics can be created. And these things work around 200 to 200 Kelvin or so. But it's a single photon number is our photon detection. We have various different platforms, and now this kind of two-dimensional material-based single photon detection is there too. I would like to stop here. I would like to stop by saying that, look, as far as our devices architectures are concerned, there's a huge amount of work that's going on, including in my group. My group looks at not only this photon detection, electronic aspects, and noises. We are also looking at using these unique device configurations for other kind of applications, which can come important to peripheries, as well as thermoelectric properties, which can lead to microwave photon detection and so on and so forth. So, and looking for architectures, particularly the neuromorphic architectures, which could lead to peripheral electronics of different sizes. Okay, thank you very much. I'm going to stop here. So I'm on time, right?
Yeah. Perfectly. Thank you very much, Arindam, for a wonderful talk, and I covered a lot of topics. So I would like to open the session for discussion. If there is somebody wants to ask any questions or clarifications, please unmute and ask. What happened?
I have questions. Can I ask?
Yeah, please.
Okay. Just a second. Uh, Thank you for your talk. My question is, could you please inform, this is a clarification question, could you please inform whether acousto-optic effect used in quantum technology or not, or acoustic frequency is low and it slows down quantum operation, that is why it is not considered?
No, actually, there are several places where quantum applications, particularly sensing metrology, including making qubits, people use acoustic frequencies in order to make potential profiles. For example, in piezoelectric systems, you can use surface acoustic waves, for example, which leads to formation of qubits or formation of quantum dots. And those could be used as qubits, or B, you can use them for electron pumping for one electron at a time from one quantum dot to another, and measure and create a metrology, surface acoustic wave based metrology for current. Okay, because then if you can, using acoustic waves, the quantum dots you form, and that allows you to create one electron at a time, you get current is proportional to electronic charge multiplied by the frequency. Okay, so that can lead to a whole new kind of operation. So certainly acoustic waves and technology is very important for quantum applications. It's very broad field, so
Mm-hmm. Mm-hmm. Okay. Another question, again, clarification, kind of. So you have shown single photon detectors. So what about 2 photons, 3 photons?
Yeah. So this is something which, again, we are looking at a particular technology, but there are other competing technologies as well. We are looking for making single photon number dissolving detectors using two-dimensional layers. And you can see this data here that we obtained some time back, nearly 4 years back. So you can see that the change in current in our detector is proportional. You can get changes in current directly proportional to the number of photons. This is essentially a Poissonian statistic from an emitter, which produces a random number of pulses. And you can see that you can differentiate between 1 photon pulses, 2 photon pulses, 3 photon pulses, and so on and so forth. So you can make different photon numbers estimation from the current changes in two-dimensional frequency.
Okay, I meant why they are so popular, single photon, as compared to 2 photons, 3 photons. So yeah.
Oh, okay. No. Wait. So I think we call it a single photon detector, but at the end of the day, your single photon is it's a nomenclature there in some form, because you would like to have detectors which will tell you how many photons are there in a bunch of light or a pulse of light, right? For many of the technologies can actually tell you whether there is a photon or not. These are called click detectors. Okay, so you will not be able to tell whether there is a single only 1 photon or multiple photons in the pulse of light. But it is sensitive to 1 photon. So those are single photon detectors without number resolving properties. But there are photon detectors which can detect 2 photons. There are, I mean, the bosonic, all these Gaussian boson sampling experiments have been done in which the photons can be 20 photons can be detected in a single pulse.
So these are
thank you.
basically avalanche photodiodes, but basically the amplification is done later once the detection is done. So that's the there can be like single photon avalanche photodiode and non-single photon avalanche photodiode. Both are available.
That's correct.
Market. So
yeah.
Right. So any other questions?
Thank you.
Hello.
Yeah.
Hello, Arindam. This is Satyaprakash from IOP.
Hi.
Hi. So it's nice talk. Actually, I would like to get your comment on this noise that you are discussed about this photodetector. So, as far as the fabrication is concerned, what are the issues that involves or that are the issue that we should look upon that can, effectively have some direct effect on controlling those noise?
Right. So we found there are, okay, it depends on which material you're talking about. As far as noise is concerned, we have looked into two classes of systems, semiconducting and two-dimensional materials-based systems for many years. What we understand is that dark current is the main source of noise, because dark current leads to, and if you have got a metallic platform like a single layer graphene as a platform for optical detection, your dark current is very high. As a result, you will get 1/f noise, you will get shot noise, and they will create trouble. So you need to reduce the dark current, which is why we used which is why we just used bilayer graphene and reduce the dark current. But that's not all. Contacting strategies is one of the important aspects that many people leave out. I mean, contact resistance is one of the big problems in electronics, but the contact noise is something which many people often undermine very badly and I think very incorrectly. And that needs to be understood. So for silicon, gallium arsenide, and these kind of materials, the contacting strategies have been developed over the years and they're very well known. But in the case of graphene and other two-dimensional material-based quantum devices, for example, if you want to make a qubit on bilayer graphene, you've got to do something about making contacts which are very low noise in nature. And there are contacting strategies. For example, you see here what we have done. This is called edge contact. Essentially, what you do, you don't put contacts on the surface of graphene. You make contact from the side of it. You etch it down, you open the atoms, the carbon atoms, and you make the metal atoms interact with the carbon atoms from the side. So that seems to reduce the contact noise quite a bit, and we found good results. But yeah, so I would say that single crystal environment is number one. Or crystalline environment, which is why you need a molecular beam epitaxy. You need high quality environment where there is no traps, no dangling bonds around. Number one, good quality contacts. Number two, and polycrystallinity, etc. Number three. So these are the three major issues which should make a high quality device for quantum applications.
Yeah, and secondly, because when we were talking about this MOS2 graphene hybrid structure, this was basically vertically stacked structure. So there, we know this angle plays an important role when it comes to transport property. So I know it's a tedious way of getting into and knowing the exact angle, but theoretically, people has been established that when this angle changes, you have different electrical property might emerge. So what would be your comment on this issue?
I'm sorry, you're saying that that in the case of twisted bilayers.
Yeah, when you have twisted bilayers, say graphene and MOS2, and depending upon what is the angle of twist, that could be change in the electrical property as well.
Right, right. So I mean, okay, graphene and MOS2 twisting is relatively less common simply because the two have got 20% mismatch in the crystalline crystal structure, and as a result, what happens is that your twisting will make the system the lattice orientations become divergent, very fast. The problem happens when you have got two same materials of similar lattice orientations, which are twisted with respect to each other. Right. So, for example, twisted MOS2 and WS2, or graphene and graphene twisted bilayer graphene, for example. So there is a whole new property that start coming up, and I think we are talking about a wealth of information and work going on in the quantum domain in these twisted bilayers of two-dimensional materials. And yeah, I mean, I think looking at the different new phases that is coming up. You never know what's going to come out in that. New type of superconductivity, for example, p-type, whatever it is, a new type of correlated phases. And so all these probably will, a new type of magnetism, for example. So these are areas which is completely new, completely uncharted, and we need to understand that, and maybe new applications to quantum will develop. I don't know. It's difficult to
Yeah,
say.
thank you very much.
You're welcome.
Okay, any other question? If not, like we are already out of time. So thanks, Arindam. Thanks a
Thank
lot.
you.
For Satyaprakash, would you project your this thing slide?